So we want to know what this graph looks like. You could always plug in some numbers to test it, or you could keep in mind that this type of function, where it's a square root and it's a constant in the front and it's minus x squared in the back, it's a semicircle every time. Or another way of doing it is like the first way I said. Plug in x equals 0, you should get out y equals 2. So that's a dot on the graph. If you plug in x equals 1, you get y equals square root of 3, so somewhere a little bit lower. If you plug in x equals 2, you get y equals 0. So at 2 on the x-axis, we should get 0 on the y-axis. And same thing if you plug in x equals negative 2. So it's making a semicircle as you plug in those points. So we're supposed to find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So this is the curve, and then we're given y equals 0. So these are all the points where y equals 0. So this is the region that's bounded. This right here is the region bounded by those two curves, and we're supposed to rotate it around the x-axis. So you're thinking about that semicircle getting revolved around the x-axis. Just checking to make sure, because okay, yeah, we're good to go. Right, so it should make something like a sphere, right? You're imagining this curve rotating towards you, towards your screen, and then rotating away from you, and then rotating all the way around. So that x-axis is that point of rotation. So to find the volume of these types of shapes, what we're going to do is we're going to create right cylinders that have an infinitely small height to them. Okay, so here's a right cylinder. Normally, to calculate the area, we take the area of the base, pi r squared, the area of that circle, and then multiply it by the height. Okay, but if we were to take a right cylinder with like a height of 1, I'm putting this figure on its side. Look, this is also a right cylinder, right? Okay, that's a right cylinder on its side. Same thing. This would be the height in this case. Okay. So if we took a right cylinder on its side, sorry, it should go all the way through because the graph is getting rotated. That right cylinder would approximate the volume, but it'd be off a little bit if it has any sort of height to it, if this has any length. So you could take that right cylinder out, you could find the volume separately. Oops, this one's on. One of those should be, okay, that's a right cylinder. It's like a Coke can that you've laid down on its side. Okay, so if it has a height of 1, then we're going to have some error because we're going to be missing the volume that's getting rotated up here, right? So what we're going to do is we're going to take an infinite amount of right cylinders. We're going to use calculus to find the volume. So in order to do that, we just need to come up with an equation for the radius and for the height. We need to come up with variables there, and then that'll be the equation for the volume. And then we can integrate that volume. We can integrate it from negative 2 on the x-axis to 2 on the x-axis. So the volume is the radius squared times pi times height. So that radius is changing. I drew my right cylinder here, but we could have drawn the right cylinder down here. Right? There's another right cylinder. So that's a smaller one. The radius is smaller. So the radius is constantly changing based on where we are on the y-axis for this curve, and that's that function that I just drew. So the y values of the radius. So it's pi times the radius squared, pi r squared, and then h, that's the part that we're saying we're actually finding an infinite amount of right cylinders. So h is actually dx because h is the infinitely small, infinitely narrow right cylinders that we're creating. So we've got our pi, we've got our r squared, and then dx is representing our h because we're talking about an infinitesimally small area. And now we're ready to do the calculus. Okay, that's definitely the hardest part because at this point in the course you're probably ready for evaluating this integral. So it's the square root being squared, so we'll get rid of that. And then when we evaluate an integral, it's a linear operator, which means it it's not exactly the same, but it acts like the distributive property. You can apply it to both. So the antiderivative of 4 is 4x. And I need to evaluate my limits of integration there. Minus the antiderivative of x squared is x to the third over 3. And limits of integration. Don't forget to multiply pi to whatever your result is. So in here, if I plug in 2, 4 times 2 makes 8. Then I need to subtract what happens when I plug in negative 2. So 4 times negative 2 makes negative 8, so that's minus a negative 8 here. And then we're subtracting whatever this result is, so I got to protect the result in another set of parentheses. If I plug in 2, 2 to the third is 8 over 3. And then I subtract what happens when I plug in negative 2. I'm going to get negative 8 over 3. So 8 plus 8 makes 16. And this is 16 over 3, so we're subtracting 16 over 3. So getting common denominators, that's 16, 32. It's 48 over 3 minus 16 over 3. So that's 32 over 3. So 32 pi over 3 is the volume of that region they've described.